Hello, I'm Ukyo Tobushi Tazawa, an author of the paper entitled Synaptic Pruning Facilitates Online Bayesian Model Selection. Let's begin the quick tour of this work. Imagine the task to predict the next position of these balls. To do this, you have to know the current position and the velocity of these balls. On the other hand, the color and texture of these balls has nothing to do with the next position. You know this fact from your experience. But someone, believing the causal structure like this, will fail this task, without doubt. So the variables in the environment shapes the structure, and identifying the structure is essential for the brain to recognize and adapt to the environment. But how does the brain perform this structure learning? This remains unclear. In this work, we address this question. Our paper is based on the theory called the free energy principle. This is the theory saying that the brain increases the predictability about the external world by minimizing the free energy, thereby performing variational Bayesian inference. And this is the typical situation we are considering. There are hidden states. In this example, this is the human's emotion, and the agent has no access to it. And the states show some dynamics following the transition rules. And yet the state itself is not observed. It is mapped into the accessible observations here. In this example is facial expression. And the task here is to infer the hidden states and the parameters that governs the dynamics of external world, that is transition rule and likelihood mapping, based only on the observations. And the theory states that the brain has the generative model, that is, the joint distribution of S, O, and theta. In addition, the brain is believed to optimize the posterior beliefs about the hidden states and the parameter to minimize the free energy F. Within this framework, the question I raised in the previous slide can be rephrased as follows. How does the brain obtain the generative model that appropriately reflects the structure of the environment? Our work provided one answer to this question. First, let me introduce the very important previous research that has shown the equivalence between the neural network dynamics and the free energy principle. Here, the two worlds are considered. The first one is neural network dynamics, and the second one is variational Bayesian inference. Here is a recurrent neural network that receives the feed-forward sensory input. And the neural activity dynamics in the recurrent layer is written as follows. Here are recurrent, feed-forward synaptic input, and recurrent synaptic input, and the firing threshold. This is derived from the famous Hodgkin-Huxley equation. And there is a generative model in the variational Bayesian world, where the agents infer the hidden states based on the information of observations. And the previous work has shown that there is equivalence between them. And this equivalence is based on the cost function of these two worlds. The cost function for this neural network can be derived by taking the integration of these dynamics. And the cost function for variational Bayesian inference is the variational free energy. And by carefully looking at these two cost functions, we can find that this variable corresponds to this variable, this and this, this and this. Like that, there are one-to-one mappings between all variables in these two worlds. This is what this equivalence means. In our recent work, we introduced new variables in this dynamics that model the process of synaptic pruning. These new variables C's here represent the probability of presence of synapses. Because these variables, these are matrices, are multiplied to synaptic weight matrices. When C is equal to 1, it means presence of synapses, because multiplying 1 to any number doesn't change that number. On the other hand, when C is equal to 0, it means the absence of synapses, because multiplying 0 to some elements in weight matrix remove that element from the neural network dynamics. And then we derive the cost function of this revised neural network dynamics. Of course, new variable appears here in the cost function, and then we can identify the versional free energy that formally correspond to the new cost function for neural networks. And finally, we can reverse engineer the derivative model behind this versional free energy. And it turned out to be that the synaptic pruning corresponds to pruning connections in the generative model that we call model pruning. In very short, we found that the synaptic pruning is equivalent to the generative model that is capable of selecting the generative model itself. Therefore, we can reach the Bayes optimal model selection rule by driving belief update rules that minimize versional free energy. So let's find the rules. And the strategy is very simple. In this figure, the horizontal line represents model parameter theta, and the vertical line represents the free energy F. For this landscape, if we update the model parameter following gradient descent, we can reach the minima of the free energy. And at that point, this equation should hold. Very fortunately, for the free energy considered in this work, this equation is analytically solvable. And here I show the solutions. There are 5 parameters out there: the posterior belief about the hidden states S, and the posterior belief about the matrices that represents a likelihood mapping and the transition rule, and the graph structure of the model that denotes the structure of the likelihood mapping and the transition rule. And the update rules are shown in element-wise manner. For example, this one shows the update rules for nth elements of the posterior beliefs about the hidden states. The most important ones are these two. These two equations provides the Bayes optimal model selection, and we term this model selection scheme Bayesian synaptic model pruning, in short BSYMP. Throughout mathematical analysis of this update rule, we found that BSYMP have very nice properties. That is, the parameter C will become 0 when the observation is independent of the states. So for example, there is a state and the 2 observations here. In the external world, the state is mapped into the first observations, but not into the second observations. Therefore, the brain should retain the connection between them, but should cut this connection. Our mathematical analysis showed that BSYMP guarantee the removal of this unnecessary connection. So I repeat the finding. Our analysis means that the connection in the model are pruned when the corresponding connections do not exist in the true generative process. In very short, it guarantees the pruning of the unnecessary connections. Here, let's look back the task to predict the next position of the ball that I've talked about at the beginning. In this task, the agent or the brain is guaranteed to learn that the color and texture has nothing to do with the next position of the ball by following BSYMP. Here comes a summary. First one is about the introduction. It is essential to select the generative model for appropriate Bayes inferences, though how the brain achieves that model selection remains unclear. We propose the Bayes optimal model selection scheme that is mathematically equivalent to synaptic pruning. And we proved that the proposed scheme is guaranteed to prune unnecessary connection in the model. And finally, this is not shown in this presentation because I want to make it quick, but in the paper, the proposed method was confirmed to outperform the previously proposed Bayesian model reduction method that has been famous in the community. In the end, I want to share the remaining questions. Here I show again the equivalence between neural network dynamics and Bayesian inference, and the synaptic pruning dynamics that we've derived in this work. In biological sense, this equation says that synaptic pruning is controlled based on the similarities between the current synaptic strength that correspond to this term and its change calculated by the Hebbian rule that correspond to this term. And here comes the question. Does the brain really operate according to this equation? As you might know, theory and actuality are two different things, so we should verify or validate it. If you're interested in, please casually contact me. I will be very happy to discuss something, or hopefully start a collaboration research. This is the last slide of this tour. I have two take-home messages. First one is for neuroscientists. Our study provided the theoretical foundation to claim that synaptic pruning is neuronal substrate of the model selection or structural learning in the brain. And second one is for engineers. Bayesian, our scheme, guarantees that the generative model will be simple, and presumably not simpler than necessary. I've questioned our methods Bayesian cause I wanna say this line. Well, that concludes my presentation, and see you soon in another tour on my future work.